in a construction of a quantum degenerate system to produce a mixture of sodium potassium atoms to realize experiment on quantum turbulence. So, that's okay, yeah. Okay, well. Okay, this is not connected. No, okay, I change here. Well, our principal motivation of this work is construct a system that in which we can able to produce boson-boson mixture or Fermi mixture, because we are dealing with two species. So the potassium has three isotopes, and we can change between 41, potassium 41, potassium 39, and eventually potassium 40. So in that system, we want to produce a vortex lattice to study the quantum turbulence when this vortex lattice can decay, and explore the vortex dynamic in the two interacting atomic species. So this is what we want to obtain. This is an example of this paper here. Okay, this is in this article. So in the left column, we have one species, and in the other, we have the second component. When the phase of each component are overlap, we have the vortex in the two components in the same circle. But if the interaction is repulsive, we can go and see the phase separation between a vortex lattice in one species. So I going to see the other species localized in the vortex in the other species. So how we are going to do that? Well, this is our experimental system, the vacuum system. So we load the two species from a 2D chamber here, and we load in the atoms in the three chamber, which is a configuration in 3D MOT. So in this chamber, we load the potassium and the sodium atom in each side, and produce our two modes. This is for sodium here, and this is the mode of potassium. They are together in the same place, so we have to misalign a little bit each mode to have the both of them sharing the same space. But we have some issue here that our potassium mode have a very low number of atoms, because we are using the natural abundance of each of these species. So this is more or less the experimental sequence that we want to implement to produce the quantum degenerate mixture. So we prepare the 2D mode from potassium and sodium separately, and we load the 3D mode for both species. We do the procedure of laser cooling to cool down the temperature more than we can. So we implement the gray molasses to reach from a 5 millikelvin the temperature of the potassium mode to a few microkelvin, only with the gray molasses process. And we are planning to do the same with the sodium atoms. So in this stage, we are able to load in the magnetic trap a very cool sample of both species in order to maximize the number of particles that we need to store the evaporation process. So after that, well, we are going to do the evaporation cooling, in which we are do the sympathetic cooling to cool the potassium atoms using sodium atoms via collision in the trap. So when both species are together, we are going to transfer that mixture in an optical dipole trap, in which we are to turning on the interaction using the phase bar resonance, but we have the possibility to work independently each species. For example, if we are work only with sodium, we can achieve the BC of sodium separately, or the potassium independently, one in other. So this is the evaporation cooling process of the potassium atom. So we are already we are sodium BC in the plug trap. So this is the difference between the effect of the plug being in the magnetic trap. We avoid the losses, putting the plug being at the center of the trap to avoid the Majorana losses. So this is the way that the atoms follows after we get a more efficient evaporation process, cooling process. This is the effect of remove the hottest atom in the magnetic trap until get the BC of sodium. So, but the problem is that in the next steps, we need to put an interaction with the pen of the a strong magnetic field like the phase bar resonance. This is the reason that we have to transfer our atoms into our optical dipole trap, a pure optical dipole trap. So this is how we see the sodium atoms in our optical. This is the top view, and this is a lateral view of the atoms confining in optical dipole trap. And we are also we produce our BC of sodium atoms with a very pure condensed fraction. We have a number higher than 19% of condensed atoms of sodium. So our thermal parity is very low, and we are already have the sodium BC in both traps, but we are already measured also the critical temperature of the BC of the superfluid. So we have our BC in the optical dipole trap, and we focalize a blue detuning beam at the center of the BC. So we create a repulsive potential here, and we move this beam along of the BC. So instead that we insert energy in the system. So, okay, sorry. This is the criterion of the critical velocity, which is the minimum of the energy for each moment divided by the moment. And okay, sorry, I lose some. I lose the graph. I'm going to show you here. Sorry. Okay, I lose. Sorry. I'm going to put here. This is better. Where is? Okay. Okay, here is better. Okay, this is the measure of the critical velocity that we do in the way that we move this beam with different frequencies and different amplitude. So we can see, as Ellen showed in his presentation, that we have two regimes in which when we introduce a low velocity into the system, we cannot create excitation like here, which this is the condensed fraction of the atom, but when we cross the critical value in the velocity, we start to create excitation, and we start to lose the condensed fraction. And these curves are for different wave amplitude and frequency of this moving in the BC. So we know which is our critical temperature velocity, so we know how are the minimum parameters that we need to put into the BC to create excitation. So This is the experimental sequencing in which we produce our vortex lattice. So we have our BC into the optical dipole trap waiting, and we're turning on this. Okay, this is supposed to be rotate around the BC like this, steering, and we release this this cloud after some milliseconds, and we can see the difference between put an excitation on the cloud and put anything. So we can see our vortex lattice, the abricot lattice is a triangular lattice here, and it's a result of input the excitation, like a steering. We can see here how this vortex lattice depend of the frequency of the input energy. If I can like a threshold here, because when I going to increase in the frequency, I can get more and more vortex, but at certain point here, we start to lose some atoms, which is when the frequency of the steering is higher than the trap frequencies. So we start to lose atoms and get the BC heating, and we can now nucleate more vortex like this. But we do some measure about the lifetime of this vortex, just to see how much time we have to do some experiment with the vortex lattice. And we find that we have around 600 milliseconds, which is time enough to do some experiment on it. But this is only result for sodium atoms, but we need to produce a quantum degenerate mixture. So, but at the moment, we have some working on this sodium species. Now we are working on the potassium, because this is a work in progress. But this is a result of our gray molasses technique, just to cool down. This is the Fano profile in which we cool our MOT of 5 millikelvin from the MOT to a few microkelvin, which is around 60 microkelvin. Now we have 20 microkelvin, which is which increase the density of the cloud, and we are all ready to put both of them together. We need to prepare also the both species to the same state, which is 2-2, just to avoid the collision between spin collision into the magnetic trap, and do the sympathetic cooling process, just to not lose atoms, the potassium atoms, when I cool down the sodium atoms. So finally, we have to put the interaction on the species and try to reproduce the figure at the beginning, in which we can put a repulsive interaction or attractive interaction between the species and try to produce this mixture. Thank you. Okay, about the conclusion. I forget it. But well, we are constructing our system, because we are already mounting stuff and fixing laser and going on. But this is what we have so far. And okay, we measured this critical velocity, and we produce this vortex lattice already in the sodium BC. So they are waiting just to cool down the potassium atoms to put to combine them and see what happens when we turn on the interaction. So well, now, yes, thank you.